Good morning, students. Today I am going to teach you fifth unit of control system, that is time response analysis. This unit is very important. It's very important, this unit. This unit, if you understand further units, it's very easy to understand. And this unit will at least I will take 5 to 6 lectures to complete this unit. Okay, before going to start time response analysis, I just recap what we have studied last unit. So what is the last unit? Last unit is mathematical modeling. Last unit we have studied mathematical modeling. Mathematical modeling. Last unit we studied mathematical modeling. So why mathematical modeling? How you going to make mathematical modeling? So you take any physical system, what you have studied last unit, you take any physical system, it could be electrical system, it could be mechanical system, it could be thermal system. So whatever the system, first to make a mathematical modeling, first you have to apply physical laws. First step is you have to apply the physical laws. So since we are electrical engineering, so we are more interested with the electrical system and also partially mechanical system. So when you talk about electrical system, you have to apply the Kirchhoff laws. The mechanical system, you have to apply Newton's laws. The first step is the physical laws. You have to apply physical laws to the system. After applying, the second step is, after applying physical laws, you will get a differential equation. After you get the differential equation, you have to apply Laplace transform to this differential equation. After you apply Laplace transform to the differential equation, you will get algebraic equation. You get the algebraic equation. From the algebraic equation, you will get Laplace transform of output by Laplace transform of input, that is equal to transfer function. So to make a model, you have to apply the 4 steps. The first step is you apply the physical laws, and second step is, after applying physical laws, you will get differential equation. After getting differential equation, you apply the Laplace transform to differential equation. So when you apply Laplace transform to differential equation, so you will get algebraic equation. From the algebraic equation, so you take Laplace transform output by Laplace input, so you will get transfer function. So this is a mathematical modeling, right? After you getting a mathematical modeling, what are you going to do with this model, right? So after getting mathematical model, you have to analyze the system. You have to analyze the system by giving different inputs. For example, you have 2 mobiles. One is Oppo mobile, one is MI mobile. So how we are going to analyze this system, right? So you just operate and you check it, right? You give the different inputs, and finally you come to conclude that this mobile is good. In another example, you take 2 vehicles, right? You take a Innova, you take a Benz car, you just drive it and you give the different inputs and you drive it. So you come to conclusion that, so one of the car is the best, it will be the good response. Even so, if you want a driving license, what do you do first? So you will go to, you apply the driving license, then after that you will be called for driving test, right? So during the driving test, so the driving test inspector, so will give different instructions, right, and different inputs. So he will give. So after, so he will see your performance. Based on the performance, so he will think of giving license or not. So he will check your performance. So the first thing is, in the time response analysis, you should have model. right? After getting a model, so you are going to analyze the system. You are going to analyze the system. So we just see here the learning objectives in this time response analysis. So these are the learning objective of entire this unit. The first learning objective is that at the end of this lesson, so we will able to learn, you are able to study time response for standard test signals. Time response for standard test signal. The test signals are like step signal, ramp signal, parabolic signal and impulse signal. And also you will able to find out parameters of second order system like settling time, peak time, maximum peak overshoot, right? And you are able to find steady state errors and static constants. So in this fifth unit, so we are going to study of all these things, right? So I'll remind you again, time response analysis means you are interested to analyze the system. Here, see, if you take any system, this system is subjected to some input. So after you giving input to the system, you will get the response. So that is how, let's say this is C of t and this is the t. So this is the input, okay? So for example, you will get a response like this, right? So as title says, time response analysis. So your response is in the time domain, right? Your response is in the time domain. So you are going to analyze the system in time domain, right? So I just recall you. So time response analysis, what is important? The first thing, you need a mathematical modeling. Once you get a mathematical modeling, so you are able to analyze the system as given before examples, right? So now the time response divided into two parts. The time response divided into two parts. So the first one is transient response. And another one is steady state response. Transient response and steady state response. So generally you represent transient response as T, Y, Ts. T stands transient, S stands response, okay, transient response. And this one steady state response. So YSS, steady state response. Of course, this is the function of time. This is also function of time. So overall system response, that is Y of t is equal to YTS plus YSS t. So this is the system response. The system response contain one is the transient response and steady state response, right? So what it is? So how the response look like, right? I'll just explain you. So if you take a system, so this is the system output, the system response, So this is the input and this is the output. In the y-axis is the output and this is the in the x-axis the time. So for example, you give a input. So you got a response. Like this. So what happened? You just concentrate. This is the input you are giving the system. I mean, you say that this is your control system. This is your control system. So you were giving input. So you get output. So you say output is a response. Also we can say. So for a given input, for a given step input, so you got a response, this kind of response. Now here you see from this portion, from this point to this point, we say it is a transient response. It's a transient response. So after transient, what happened? It becomes stable. So this portion, from here to this portion, so we call it steady state response. You see the transient response as t approaches, to infinity, as t approaches infinity, the transient will die out. Right. So this is steady state means after transient, so it will be settled. So that portion is called steady state response. So time response has two components. One is transient response and another with the steady state response. So final response. So you will write as y of t is equal to, so y t r t plus y s s t. So this is the total response of the system. Now we are going to study test signals. We are going to study about test signals. Standard test signal. So this standard test signal you are going to apply to the system. You just talk about a power system, right? And a power system, sometimes the input signals are unknown. And again, missile tracking system. So the input signals are unknown to us. In some process control, so inputs are known, but in some control systems, the inputs are unknown. But you see, if you see the power system, if you see the evening, what happened? So everybody switch on the lights, everybody switch on the fan. So what happened? So it suddenly will rise, right? And also then the midnight, so 12 o'clock, all switch off the lights. So it will gradually system will go down. So the load will go down, right? So it means in the even mobile, missile tracking system also, when the enemy coming to our country, right? So we don't know how control system going to react. That input unknown to us. The enemy is coming to our field. That input is unknown to us, right? So, but however, so some of the inputs are we just approximated that. So most of the inputs, these kind of inputs, our system will come across. Our system will be subjected to these four standard test signals. What are the four standard test signals? The first one is standard test signals. The first one is step signal. The first one is step signal, and the second one is ramp signal. And the third one is parabolic and the fourth one is impulse. The fourth one is impulse signals. Of course, the fifth one is also sinusoidal signal. So this you are going to study in a frequency response analysis. So in frequency response analysis, so our control systems deal with in a frequency. See, all communication systems, all communication control systems, we are interested to deal with the frequency. There we are going to study sinusoidal signal. At presently, we are going to study these four input signals. So step signal, ramp signal, and parabolic signal, and impulse signal. So first we see the step signal. So the step signal, we just see the graph. So a step signal, you just see here R T here, and this is R of T. R of T is an input signal. So this is step signal. So this is a means amplitude A. At t equal to 0, it rises, right, and it maintain constant. You see this thick line. This is the step signal. So at t equal to 0, suddenly rised at the point A and it's maintained constant. So this is a step signal. So R of t is equal to A, right, for t greater than or equal to 0. So when t is equal to 0, it rises to this point at all t greater than 0 values, so it maintain constant, right? Then R of t is 0 elsewhere. R of t is 0 elsewhere. So this is the step signal. If A is equal to 1 here, if A is equal to 1, we say it is a step signal. So I just going to draw a graph here. So this is R of t. So this is A is equal to 1. So this is called a step signal. We call it unit step signal. So next we are going to study the ramp signal. So this is the ramp signal. We see the graph. So this is a t and this is R of t. So ramp signal, so it is a 0, t is equal to 0. So it has this kind of slope, ramp signal. This is the ramp signal. So R of t is equal to, here R of t is equal to t into E of t. T into E of t, right? So when t into E of t, so this will be R of t is equal to t into E of t for all t greater than or equal to 0, right? T greater than or equal to 0. Starts t is equal to 0, t is equal to 1, so it will increase. So E will have a slope like this. So this is a linear graph you will get. So even you apply the Laplace transform to this. So when you apply the Laplace transform, so what do you get? Apply Laplace transform. So before that, here I missed one thing. So R of t is equal to t into U of t for t greater than or equal to 0 and 0 elsewhere. So in all other places it become 0. So when you apply Laplace transform to this, so R of t, Laplace transform of R of t is equal to Laplace transform of t into E of t is equal to, so you say 1 by s square, right? It means R of s is equal to, so 1 by s square. So this is ramp signal. ramp signal graph, right? And also you can multiply with the a also here. If you multiply a, so you can also put here a by, finally you will get a by s square. So this is the magnitude of this slope. Magnitude could be 1, 2, 3, so it can be changed. So next we see the parabolic signal.